Everyone. I'm very pleased to have Jonathan, Professor Dushoff with us. Jonathan is a member of the Network Mathematics for Public Health and a key member in the Canadian network of mathematical technologies for public health. Jonathan, Professor Dushoff is a theoretical biologist with particular interest and established authority in the field of evolution and spread of infectious diseases and impact humans. And this giving excellent positions to talk about the conceptual models of immunity. I just want to, before handing over to Jonathan, I want to advise the audience that if you have questions for clarification of the presentations, you can post those questions through chat. Otherwise, I would encourage you to defer questions until the end of the lecture. Thank you, Jonathan.
Thank you very much. So I'm talking today about work that's very much in progress, and maybe it'll be short. And if it's short, maybe we can have a good conversation about it. I've, like many people, got caught up with a lot of COVID-related questions, and now very interested, of course, in what's going to happen in the first North American flu season now that the COVID pandemic is no longer a pandemic, or whatever the official word I'm supposed to use is. So we've been thinking a lot about immunity, and I've been thinking thoughts about immunity that tie to thoughts that I've been having for quite a long time. Starting maybe 20 or 30 years ago as a graduate student, when Julia Gog was constructing mathematical frameworks for cross immunity to think about coexistence of influenza strains and the patterns of influenza evolution. But these ideas are broadly applicable to interactions between different viruses and also interactions, for example, between different strains of COVID or flu. I'll post these slides somewhere through the fields, and there's a link here. So I've been trying for a long time to think about the conceptual underpinnings behind the mathematical ideas, different ways of treating different strains. And I've been working, among others, with the Public Health Agency of Canada, and thinking about how to model COVID immunity has made me start sharing these ideas more widely. And now we're turning it into some sort of research project. And there's a link to that pre-publication as well. So very often we think, when we're talking about vaccines, we think that vaccines may be leaky or vaccines may be polarized. So a leaky vaccine means that everybody who is vaccinated is treated, at least in our model, about the same. And the protection works the same for everyone. Whereas in a polarized model, we sort of assume, well, the 80% efficacy means 80% of the people are just protected from the disease, and the other 20% are not. And many of you will have seen models of this type or seen this sort of construction. We can ask a couple of things. I always try to remind myself and others that if we're talking concretely about protection, it almost doesn't make sense to do that without an endpoint. And it's something that we very often leave out. The early COVID trials mostly measured protection against death and severe illness, and there was a lot of rhetoric around that and how it related to messaging around disease and infection. We might also ask whether a vaccine protects me against transmitting the disease to others, whether it protects me against having a measurable infection at all. Perhaps, and this is key to modeling frameworks, perhaps the vaccine is going to protect me so much that when I'm challenged, I don't even have an immune response, and therefore I don't have any boosting of my immunity to the vaccine. So I mentioned Julia Gogg in her earlier work about immunity and cross-immunity. There are strong links between these paradigms of polarized and leaky vaccines and Dr. Gogg's introduction of history-based versus status-based models of viral competition. So a history-based model means what we need to know about a person is what viruses or what strains they've been exposed to, been infected by. And then we're going to calculate based on that what happens the next time they're challenged. And this is very strongly analogous to leaky immunity. If I know what vaccines you've had, or if I know what strains of flu you've had, that's what I need to know to decide what's going to happen next. And the alternative framing is status-based, that when I get a particular influenza, I'm going to have a particular immune response to it. And what the modeler should be following is my personal status, typically defined in terms of which related flus I'm now immune to based on the exposures I've had, rather than a list of the exposures. And this is more or less exactly analogous to polarized immunity. So I'm going to talk mostly in terms of vaccination for the next 20 or 30 minutes, but keeping in mind that these are exactly the same questions that we need to ask if we're thinking, for example, about competition or interference between different respiratory viruses, or perhaps more relevantly, interactions between strains of SARS-CoV-2 or interactions between strains of influenza. So here are some pictures that we did for our preprint, showing a classical view of leaky immunity at the top and a classical view of polarized immunity at the bottom. So in leaky immunity, rho is the rate at which we're vaccinating people. I'm assuming people can see my mouse and this little weird flashlight thing, so please tell me if not.
We can see it.
Thank you. I was hoping you would tell me you can see it, because then I feel like there's people listening. If nobody had answered me, I would say, am I even talking to anybody? So thank you. So here we're vaccinating people at a certain rate, and in the leaky model, they all go to this box. And then once they're in this box, they sort of feel the force of infection less, right? So the force of infection is effectively reduced by the amount of vaccine efficacy. The alternative is a polarized model, where as soon as I vaccinate you, you'll either move to a new susceptible class where you're equally susceptible, but you already think you're vaccinated, so I'm not going to vaccinate you again. And that's the reason why these two compartments are differentiated. So you think you're vaccinated, but you're really susceptible, or with the probability of V sub E, you're going to just be completely recovered. So those are the two paradigms. And there's a lot of criticism of the polarized approach, specifically saying that there's some proportion of people for whom the vaccine doesn't do anything at all. Their immune system just doesn't care that you vaccinated them. And this is not consistent with the kind of serological data that we have. There are certainly people who don't have what's considered to be a significant response, but of course you can't prove statistically that it's a zero response, and those numbers don't line up well with the vaccine efficacy. But this is considered to be unrealistic, and we're going to come back to other ways of thinking about the polarized approach. But the leaky approach has its own key limitation, which is in a leaky approach, I may get vaccinated against COVID, and I may be challenged a month later with the dominant circulating strain, and I may, because of the vaccine, beat it back, right? And this is now presumptively, I feel like I should switch to the picture soon, but this is presumptively in our modeling world, this is a challenge that would have infected me if I didn't have the vaccine. But now we're thinking I've beat it back, but I'm still just as vulnerable as any other average vaccinee, right? So I've just finished defeating a potentially effective challenge, and then next week I meet another potentially effective challenge and I become ill. That seems unlikely. It seems unlikely that these challenges, these V sub E sub L, whatever challenges, just disappear. It's as if I've never seen them in a leaky model. And so for many decades, I've been thinking of the polarized model in sort of a broader framework than it's typically advertised. So this is one way to look at the polarized model, is that whatever's going to happen to my immune system happens irrevocably when I'm vaccinated. But there's another way to think about it. The other way to think about it, if you're a dynamicist, if you're somebody who likes to study the properties of simple models like this and think about different ways to link them together, we could say, well, maybe this decision doesn't necessarily happen right now. Maybe it's just as if it happened right now. Maybe it's something that we're going to decide later in real life, but as modelers, we might as well flip the coin now. We might as well say, well, is this what's going to happen to this vaccinee when they meet their first challenge? And we can express this new framing in terms of a leaky model with boosting. So if we imagine that we now go back to the original leaky model, but now we say, and we can think about, I've shown here what I can call perfect boosting, which is these disappeared challenges have now been rescued. And here I'm assuming that any time I meet a potentially effective challenge, a challenge that would have infected me if I were naive, I'm going to have an immune system response to it. I might get sick and then have the immune system response to it and then recover. Or I might simply say, okay, I have the vaccine, I know how to fight you off, but get boosted to a point where I'm not going to get sick again anytime soon. And certainly we can imagine paradigms between the pure leaky paradigm and the perfect boosting paradigm. But the point here is that implicitly, this is a way that some of us have been justifying the polarized paradigm because the dynamics are the same. It may be, well, we are in fact imagining different processes happening within the individual. As population modelers, we often imagine these processes to be invisible, but we may also think about measuring proxies for those processes in terms of looking at serology of people who've just been vaccinated and looking at their serology through time. But setting aside what's happening inside people, these two models, the perfect boosting model and the polarized model, produce the same population level dynamics. So here we see a population that's going to have an epidemic, and we vaccinate some of them. I think this is a vaccinated and unvaccinated population. I'm sorry, I suddenly don't remember. But the point is that applying a leaky vaccine is going to reduce the size of the epidemic fairly substantially. This is a log scale, so I'm showing you 4 orders of magnitude. So a factor of 2 or 3 reduction in the size of the epidemic doesn't show up well on this graph, but of course is very important to public health. A polarized vaccine is going to reduce the epidemic further than a leaky vaccine would. And that's because under a leaky vaccine, there are people who are protected the first time who then go on and get infected a second time. And that effect increases as the size of the epidemic, as the size of the reproductive number increases. But if we were now take the leaky vaccine and add perfect boosting to it, so here's the polarized vaccine, here's the leaky vaccine with perfect boosting, and there's literally no difference in the population level dynamics in the time course of incidence. And that's sort of what you would expect. So in some sense, generating this graph is more a test of our programs than it is of our hypothesis. or at least I would say that if these had been different, I would have looked at the code first and not at the ideas. And we can look more broadly. So I'm just showing you a subset of the curves that we've done. So here we're imagining a new virus entering a population with a very high R0. It's about 8. And so the final size, if we let an epidemic go through this population and nobody's been protected, the final size is 99.999%, as seen here. If we now introduce a leaky vaccine, what happens here is if we vaccinate 25% of the population, we've reduced R0 from 8 to 6. So instead of 99.99% of the population getting infected, there's fewer 9s involved. But what's happening is we're getting a big epidemic and everybody's getting challenged over and over again. And so very few people are not getting infected, even though very few people are not getting infected, even though they've been vaccinated, because they're just exposed over and over again. And each time you're exposed, you flip a biased coin, and eventually you get infected. And what we've shown here is we're adding the idea of boosting, so that if 100% of of challenges are boosting, so in other words, we now have the same, I guess this is a 30% effective vaccine, I get challenged the first time. And if I'm lucky enough to be one of the 30% who's protected the first time, I now assume that my immune system is boosted. And if it's perfect boosting, I don't get sick again. So now 30% efficacy results in a 30% reduction in the number of people who are going to get infected. And here we have, just to remind all of us, that boosting doesn't have to be perfect. Here we have a curve with a 50% boosting probability. We can also model this same scenario with a polarized vaccine. In a polarized vaccine, everybody who's going to be protected by the vaccine is protected immediately. And so these 3 curves all collapse to the same curve. And I've shown it with an intermediate step, which is kind of fun, where we assume that the vaccine has some amount of leakiness and some amount of splitting, so that for a 50% effective vaccine, we have 70% or so that are going to a box where they're then 70% protected. But we see here, first of all, the really dramatic effects. If R effective is large, the really dramatic difference between these 2 assumptions. And second, we see that as we add immune boosting, this whole thing collapses, right? So the dramatic difference between this yellow curve and this collapsed yellow curve, which is the same as the difference between this yellow curve and this dark curve. So that's the basic idea, and just trying to organize thoughts around how we try to measure. I've already indicated that I'm a little dubious about concluding protection directly from serology, but certainly linking these ideas to longitudinal studies of serology is potentially useful. We can also think about measurements, and it's tempting to think that this is a good way forward, and I'll say in a minute why I'm worried about it. We can also think about these assumptions in terms of how we would expect to measure vaccine effectiveness in a population. So basically, efficacy is the kind of parameter that we put into a model, or that we might try to measure with a clinical trial and a relatively short exposure window. It's saying how much basically do I think the vaccine is going to protect me, given that I'm challenged exactly once. Effectiveness is when we try to measure protection in a population. So a group of people have been vaccinated, a group of people haven't been vaccinated, how much safer is the first group, and how do we try to measure that? So what assumptions do we make? And in particular, there are two natural ways to define effectiveness. One is we take a time window and we just count up all the people in both groups that have been infected. And so we're comparing the cumulative incidence in those groups. The other is that we can look through time and we can keep track of who's been infected before and remove them from our pool and measure the instantaneous hazard of infection given that we think somebody is susceptible. And both of these two things are commonly done. And plotting this in terms, so for the sake of, I hope, simplicity, I guess it's simpler, I hope it's sufficiently clear. These are all with the leaky model, but when we have perfect boosting, it's going to give us the same dynamics and the same answers as the polarized model, whereas when we have no boosting, it's what I would call a classic leaky model. And if we look at cumulative incidence over a period of time, in some sense, we should already know what we're going to find. So this dashed line indicates the vaccine efficacy. I feel like I should have said effectiveness here, but this dashed line indicates the assumed vaccine efficacy in our simulations of 60%. And we already know that that should match the estimated effectiveness for the boosted or the polarized model, right? In the polarized model, this is really going to protect 60% of people. And therefore, we also already know that as the epidemic goes through and the people who've been given a leaky vaccine are challenged twice, in the population that made the leaky assumption, we expect to see vaccine effectiveness, estimated vaccine effectiveness going down and being lower than what we know is the true vaccine efficacy. Or mapping back to the real world, we would expect the measured effectiveness of a leaky vaccine on this scale to be less than the measured efficacy in a controlled trial. If we do a hazard correction, if we try to look at the instantaneous risk, then we get almost exactly the same story, but slightly in the opposite direction. The hazard-based estimate matches the assumptions of the leaky model, that anybody who's been vaccinated and is susceptible is still equally susceptible and exactly as susceptible as you would suspect from the vaccine efficacy. So this number for the sort of true leaky population stays constant, and the number we expect to measure is the true efficacy. And therefore, the estimated hazard-based effectiveness among people in the polarized and or boosted population goes up through time. So that's, I told you it was work in progress. That's really what I had to tell you. I will use my platform and make a few more comments anyway. So going forward, we're very interested in modeling for COVID and other diseases, what we expect in a mixed immunity landscape. So we have people who are vaccinated for flu or COVID, or people who've been infected, or people who have both. And we have for both of those diseases, we also have the strains that are changing. I said that you almost can't talk about protection without saying what your endpoint is, but then I basically did that. And so we do want to come back and talk about the question of protection against infection. So up until now, I've mostly been talking about protection against infection and assuming that anybody infected was transmitting about the same, and sort of ignoring the question, which is the big question right now for new and different COVID strains, ignoring the question of protection against severe outcomes. There's also the question, I said that I was going to come back to why just looking at different measures of effectiveness is not going to answer the whole leaky polarized boosting question. It's because immunity is waning through time, right? If immunity never waned, then we might really be able to learn a lot by looking at the kind of profile that I'm idealizing here. And finally, something that I only started thinking of when preparing this talk is maybe a broader view of leakiness. So I've been a little biased against leakiness for the last several decades because I never liked the idea of these challenges just disappearing, right? In our model world, these challenges exist, but they just disappear. And in the pure leaky model, we don't have this bottom arrow. And I get vaccinated, and then I get an effective challenge and presumably fight it off with the help of the vaccine, and my immune system doesn't care. Tomorrow or next week, I get another effective challenge, and I'm as likely to get sick as my neighbor who hasn't seen any COVID since the vaccination. So what's the broader view on leakiness that has now confused me to a certain extent? Well, we can define leakiness as any gap between efficacy and effectiveness on the cumulative incidence scale. But the problem is that not every challenge is the same. And recently, people have been thinking about leakiness, have been thinking about it in terms of dose dependence, right? And so up until now, I've talked about the difference between leakiness and polarized and about boosted and unboosted in terms of how you respond to a series of challenges, more or less explicitly assuming that every challenge is the same. But it's not. I could be challenged with a lot of virus at once, or I could be challenged many times, or I could be challenged, I could get potentially infectious doses a day apart, or an hour apart, or a week apart, or a month apart. And I think most of us would have the intuition that the immune system is going to feel differently about those set of challenges. Here's a study that came out recently that explicitly defined leakiness as dose dependence and showed that there is dose dependent protection. I'm not going to try to talk through this slide, but basically the third bar in each of these 6 panels is higher. It's across Delta and Omicron and across various immune backgrounds. And I could raise questions with the statistics, but the overall pattern is that it looks like there's less effect of protection when you get a higher dose, which is certainly a perfectly good way to think about leakiness and raises, I think, the questions I asked prematurely a couple of slides ago, but we can certainly imagine that challenges a week apart are likely antagonistic, right? I go somewhere, I get challenged by COVID, I have some amount of pre-existing community, I get a sniffle or I get a little bit of something swollen in the back of my throat, and then I get better. Now I'm stronger, right? So that is basically the immune boosting paradigm, and it's going to give dynamics like a classical polarized model. How about challenges an hour apart? How about challenges 30 minutes apart? You know, I go from the lunchroom where I'm eating lunch with somebody with COVID to my office where I'm working with somebody like COVID. That's not the same thing. It's been the same thing in the models I've showed you, but we don't believe it's actually the same thing. And in fact, synergistic challenges may bring us back towards more leaky-like dynamics. And I'm not going to say anything about that, except that this is one of the advantages of sort of formal and simple modeling. Like trying to construct these models and ask these questions has brought me to a new set of questions, some of which may be practical, even considered practical even by non-modelers. So that's all the concepts that I feel I need to get a little straighter in my mind, because we're trying to do things like this. So these are slides that Mike Lee from PHAC has very kindly allowed me to share, even though they're very preliminary. And it's an idea of if we're trying to model COVID going forward, then we might need fairly complicated conceptual ideas of how protected people are likely to be after various exposures, either to a vaccine or to disease, and after various amounts of time, because the vaccine might be waning. And in our minds, when we're trying to think about what's going to happen with a new strain of COVID or with competition between strains of flu, what's really going on is you want to put some part of this model inside a more complicated model, inside a model of cross immunity. So here's another just sketches on the whiteboard, but here we're imagining that each of these boxes have a set of levels inside them, and that we're trying to make a model as simple as possible, but not simpler, to address some of the questions that PHAC is trying to answer about keeping alert to the dangers of a flu epidemic or a COVID epidemic. So I said I was going to finish early. I can't say I expected to finish that early, but maybe people have other things to do, or maybe people want to challenge one or more of the things that I've said. But in any case, thank you for your attention.
Thank you, Jonathan. It's nice that you stopped early, that we have opportunity to challenge you. Any questions?